Okay, this is the second video for section 1-3. And I just realized this is a little wonky in these notes. I did this example in the first video, but really we should have gone over this first. So let me quickly go over this. This is the definitions for exponential growth and decay. So this is an exponential function, and k is just a number, so it's a positive number. So for exponential growth, your base, which is a, this is your base because that's the number that the exponent, which is the variable, is attached to. That's going to be greater than 1. So for example, you should put these example in your notes. Here's the in general. K is a constant, positive. In this example, I chose 2 for my base. 2 is greater than 1, so my base is greater than 1, so this is an exponential growth. And so these graphs will have this general shape. As x gets bigger and bigger, y is increasing. Here is an example of a function that would be decay. So for up here, they say for decay, the base, a, is between 0 and 1. So it's basically a fraction that's less than 1. So here's my example. I used the same constant. So that's the k. Now here I made my base 1/3. 1/3 is between 0 and 1. So this is going to be decay. So like this half-life problem we did up here, if you graph decay, as x gets bigger and bigger, y decreases. Okay, so growth, your base is greater than 1. Decay, it's a fraction between 0 and 1. I will tell you, sometimes they try to fool you, and you might get a function that looks like this. This is a fraction, but this is still growth because this fraction is greater than 1. So be careful. Look out for that. All right, now let's talk about e. So flip over. The number e. It's just a number. And this is it. It's irrational. It goes on forever, kind of like pi, and doesn't repeat. And the reason that it's so important, and it is the inverse to the natural log. Okay, so let me just write this up here. E and the natural log, so e to the x and the natural log of x are inverses. So they undo each other. So when you're solving, you use e to undo a natural log, and you use natural log to undo an e. So they are inverses. So see what you remember about inverses. If you don't, I think there was something in the summer work on that, but you might want to look that up. So first we're just graphing this. So this is the e to the x function shifted down to, so let's think about the regular e to the x function. This is one you really need to have in your brain. It does this, and its y-intercept is 1. So 0, 1, because e to the 0, anything to the 0 is 1. So this is regular e to the x. This one is going to be shifted down to, so that horizontal asymptote that here is the x-axis is going to move down here to -2. This y-intercept is going to move down 2 also, so that's going to go to -1. And then we're going to grow. This is a sketch like that. You could probably check a few points like this from your calculator using your table. Okay, and then this is another graphing one. This is, I'm going to say it's going to grow quicker than the normal y equals e to the x. And my highly technical term for that is it's going to be skinnier. It's going to grow quicker. So it's still going to have this y, that 0, 1 y-intercept, but it's going to grow a lot quicker. I probably should have drawn it a little steeper. Let's graph it so you can get an idea. So let's clear that one. So let's do, where's that e? It's down here. It's down here by natural log because they're inverses. So e to the 2x. So let's graph that. Let's do a little better graph. Oh yeah, I need to make it way steeper. And let's get the table. So we need some smaller x's here. Oops, I'm going big. I need to go smaller. Should have had this ready before I started my video here. That's okay. When x is 1, y is 7. So let's do that point. 1, 2, 3, 4, 5, 6, 7. Okay, so this is how steep we should have this going here. And then to just show you how quick it's growing, when x is 1.5, we're up to 20. When x is 2, we're up to 54, right? So growing much quicker, and my technical term is skinnier. So the number e is used in word problems where interest, for example, is being compounded continuously. We use this formula. It's called PERT. Hopefully you remember that. We call this PERT. So it's a growth problem, but when they give you that important distinction that your interest is being compounded continuously. So this number, 2.7, this e, comes up so much that is why they gave it this special e designation. What is the formula we use for not compounding continuously? Well, you probably don't remember, but it was the initial amount. The P stands for principal, R, which is your rate, over N to the NT. So this is not compounding continuously. So P in both of these problems is your initial amount, so what you're starting with, whatever money you put in the bank first. R is your interest rate. I like that one because it makes sense. R and R. N is the number of periods compounded. So for example, if it's compounded monthly, you'd have 12 periods in a year. If it's compounded bi-monthly, you'd have 24. And T is your time. Usually when you're talking about interest, it's going to be in years. All right, so Chanel opened a bank account with 1.25 interest rate. That looks important. Compounded quarterly. So not continuously. So I'm going to use this, not this. She put $500 in her account, so that's what she started with 10 years ago and has not touched it since. How much? So we're solving for an amount. So I just like to put my what I know over here. Now the one thing you got to remember about interest rates is we always convert them to a decimal. So divide by 100 or move the decimal 2 places to the left. Percents. Cent is short for century, so per 100. So this is 1.25 divided by 100. Okay, so that's your R. Your initial amount is $500. That's what she started with. She kept it in the bank for 10 years. Compounded quarterly, so N is 4. And Y is our unknown. So now we're going to plug that all into this formula. So her final amount, y is your final amount, equals her initial amount. 1 plus 0.0125 divided by 4 to the 4 times 10. Use your parentheses carefully. You can punch this whole line in your calculator. And this is how much money she's going to have when she's done. So in this case, since it's money, you can do 2 decimal places. Don't forget your dollar signs. And then do this last part where you think, does that make sense? Started with $500, 10 years, 566, pretty low interest rate. Yes, that makes sense. If you got a number like 0.001, right, that would make sense. If you got a number like 50,000, that wouldn't make sense. So make sure your answer makes sense. Always, always, always. How long would it take Chanel's investment to double if the account was compounded continuously? Okay, so as soon as you see this compounded continuously, you're going to use this. Y equals P times E to the RT. And we're finding time. So time is our question mark here. So we're solving for this. So this means we're going to have to solve an exponential because our variable is stuck up in our exponent. And they're asking how long would it take for it to double. Well, she's starting with 500. So how long would it take for her to have 1,000? So final amount equals initial amount times e to the r. T is what we're solving for. So first step, well, we want to multiply those, but we want to isolate the variable on one side of the equal sign. So we want to divide both sides by 500. So 500 divided by 1,000 is going to be 2. So we're going to be left with this, e to the 0.0125t. Okay, now to undo an exponential, I convert it to a natural log. So this is going to be, I like to put my exponential on the left. Oops. 0.125t equals 2. Because if you had me for Algebra 2, I taught this arrow method. So to convert this into a natural log, I say natural log. Remember, natural log has the base e, but we'll write it. Natural log base e of 2 equals 0.0125t. Okay, natural log of 2, I can get that in the calculator. So there's my natural log button. Natural log of 2 is 0.6931. Let's just write that down. I'm going to go this way. So this is 0.693147 equals 0.0125t. Now honestly, I probably, especially if I were doing the AP test, I wouldn't even write that number. I would just go ahead and divide it by 0.0125. So, and then I know it's using all these decimal places, which is what I want. I never ever want to round until the end. So that's what I get, 55.45177. So these are years. So I'm going to say t equals approximately 55.4517 years. Does it say anything about rounding? No, so we'll just leave it big like that. It's going to take 55 years for this to double. She's compounding continuously. Okay, so those are fun problems, I hope. I liked them in Algebra 2. Hopefully you still like them. We do have a quiz coming up. There's some advice there to get you ready for the quiz. That's it. Thanks.